Okay, so welcome back to Unit 8. We're focusing on thermal energy and laws of thermodynamics. Okay, so let me just give you a little heads up. Please do not flinch because we're about to talk chemistry. Okay, I know chemistry is and this is an area of chemistry where a lot of students tend to struggle because we're going to have to do like conversions of moles. We're going to have to talk about the ideal gas law, right? We're not going to get into like Charles's law, Boyle's law, all those different laws, right? We're just going to look at the relationship between the pressure and volume and then equal to that constant, okay? So let's start way back in the beginning, right? So we're focusing around ideal gases. So an ideal gas is one in which the particles have no effect on each other, right? And so they're like just whizzing by each other. They'll collide, right, creating more energy and so forth. But like the air around us, most real gases are good approximations to an ideal gas. And I could not find that blank. And so I think it tends to be more like the kinetic theory or the ideal gas law, right, is the key to understanding the behavior in ideal gas. But if there are ways that we can affect the gas, so increase the number of gas particles in an enclosed space, and you're going to increase the pressure, right? So if I look at this, the number of particles, right, is directly proportional to the pressure. Why is that? Because they're colliding, creating more energy, right? So then there's more energy in there, right? And then we're increasing the temperature, okay? And then we're increasing the pressure inside. So an increase in pressure also occurs when the volume of the gas decreases, right? And so there's an inverse relationship between P and V. Okay, and so what we're really doing here, these first bunch of statements, is really kind of establishing, right, what is this relationship going to be? Okay, and so the reason why, let's say I have, it's like a piston, I have all these particles flying around in here, and then I push down on the piston and I decrease the volume. Well, now all those particles are sitting closer together, more interactions, right? What are you going to do? You're going to increase the temperature, you're going to increase the pressure. So P and T are going to go up because V went down. Okay. Now this happens because the smaller volume causes the particles to strike the container more frequently. All right. And then the other factor is heating, right? So if I heat an enclosed gas, it's going to increase the average kinetic energy, right? So the heat puts in energy into the system, spreading it out amongst the particles, and what that means is the more energetic particles will strike the walls more frequently, okay, increasing the pressure. So pressure is directly proportional to temperature, okay? So these three observations are the key observations to our equations. And so we talked about PV, right, the inverse relationship, equals the number of particles times T, right, because that's what we get here in this relationship and this relationship. But then we have this constant of proportionality, right? So we have K, right? And sometimes you'll see this equation as PV equals NKT. You can write it whichever way you want, but so N is the number of particles. K is what is known as the Boltzmann Constant. And it has a value of 1.38 times 10 to the negative 23 joules per kilogram, or excuse me, joules per Kelvin. And then T is the temperature of the gas. And one thing to note, because if you look at the constant, it's in Kelvin, your temperature needs to be in Kelvin. And V is the volume of the gas. Now, your volume needs to be in cubic meters, right? And so this, again, we need to focus on SI units. So Kelvin's the SI unit for temperature, cubic meters is the SI unit for volume, right? And so here's an example using this version of the equation. So this says a person's lungs can hold 6 liters of water, or of air, not water, that's very dangerous if a person's lungs are getting water, at 310 Kelvin and a pressure of 101 kilopascals. So if you think back to unit 5, right, we have to convert kilopascals to pascals. Given that the air is 21% oxygen, find the number of oxygen molecules in the person's lungs. Okay, and so what we need to do, right, is first thing we need to do is find the volume in cubic meters. And so the way the conversion factor is 1 cubic meter is 1,000 liters, right? So what we're going to do here is divide 6 and 1,000. So we end up with 6 times 10 to the negative 3 cubic meters. So you can see a cubic meter is a much larger space than 1 liter. Okay, and so now what we do is we take our equation PV equals NKT, and we're going to solve this for N. So we're going to say N equals PV over KT. Now this N is the total number of particles, right? And but what we want to do is notice that we have 21% oxygen. So in the end, we're going to end up multiplying that by 0.21. Okay, and so we're going to say PV, so 101 times 10 to the 3 pascals times our volume, 6 times 10 to the negative 3, divided by K, 1.38 times 10 to the negative 23, times our temperature, which is 310. Okay, and so what happens is that gives us a total number of particles of 1.42 times 10 to the 23. But again, that's total particles in the lungs, right? So we only want oxygen. It tells us that it's 21%, right? And so we're going to get 2.97 times 10 to the 22 oxygen particles. Right? They could have told us that it was like 52% nitrogen, so we would change that 0.21 to 0.52. Okay. Now, what happens is, though, at times it's more convenient to talk about the amount of gas in terms of weight, right, rather than the number of particles. So the way we measure this is that we're going to use moles. And I'm sure I'm going to bob and weave out of the way because people are going to throw things at me. But remember, a mole is the amount of a substance that contains as many particles as there are in 12 grams of carbon-12. Right? That's the official definition of a mole. Now, the number of atoms in a mole of carbon-12 is 6.022 times 10 to the 23, right, particles. And you guys may recognize this because this is Avogadro's number. Okay. Now we can change the equation to say PV equals nRT, right? So R is what is known as the universal gas constant. And sometimes people call this PIV NERT, right? Okay. Let's just say, oh, PIV NERT. Right, so universal gas constant is the capital R, has a value of 8.31 joules per mole times Kelvin. So again, there you see your temperature in Kelvin. Now the reason why you do have to convert, because the T in both these equations is not a change in temperature, but a temperature. And lowercase n is the number of moles. Okay. Now, you may have to do stuff with molar mass, okay? And so molar mass, right, I think we get into it a little bit later, or maybe it was something I did with AP Physics C, but understanding that molar mass is the mass divided by Avogadro's number, right, or something like that. It's the number of moles divided by Avogadro's number or something weird. Okay, so how many moles, not moves, sorry, there's a reason why I work in numbers, right? So how many moles of air are in an inflated basketball? Assume that the pressure in the ball is 171 kilopascals, the temperature is 293 Kelvin, and the diameter of the ball is 30 centimeters, right? And so the reason why we need this is because we need to find the volume of the ball, right? And so the volume of a ball is a sphere, so it's 4/3 pi r cubed, okay? Sorry, that's r cubed, not a run on, but so 4/3 pi r cubed is going to be 4/3 pi times 0.15 cubed, right? Because this is in centimeters, we need it in meters. So it's going to tell me that I have a volume of 0.01414 cubic meters, right? So now I can use my Pivner equation. So PV equals nRT. I'm looking for n, right? And so I'm going to solve this for n. So n equals PV over RT. So it's Piv over ERT. And so we're going to plug in our values. So again, we have to convert that 171 kilopascals. We found our volume to be 0.01414, right? R 8.31, and T 293. Okay. If this is not given to you, if this is given to you as 20 degrees Celsius, you must convert. Okay, and so then we plug that into our calculator, and we find that there's 0.994 moles, right, inside this basketball. And what they could also ask you is how many particles there are. And so like the Avogadro number is particles per mole, right? And so you say 0.994 times Avogadro's number, because that would be like our conversion factor, right? And that would tell you that there are, I actually didn't calculate this because it was a little bit of a surprise that I'm going to talk about this, but so we're going to go 6.022 exponent 23 times 0.994, and we're going to get a really big number that my computer decided not to use scientific numbers. So 3, 6, 9, 12, 15, 18, 21, 23. So it's slightly less than Avogadro's number because this is not exactly 1 mole. Okay. So in the next video, what we're going to do is we're going to look at the kinetic theory of gases. So we're still working in this temperature world and energy. Okay, and then we're going to eventually switch to the heat transfer and the more specific topic of heat.